Hi everyone, welcome to your section 4.3 notes. Today we're going to actually get into some context, I guess, real life examples of how radians are used in the real world. And they're most commonly used in their foundations in arc length and circular motion. So just reading in the top blurb, it says, in geometry we found if given a central angle and the length of the radius, we could set up a proportion to find the length of an arc in a circle. The arc length is a fraction of the total circumference, and the central angle is a fraction of the full revolution. So if you guys remember way back when, we had our circle, radius, let's say is 4, let's say this is 60 degrees. So we would find our fraction of our circle, so 60 over 360. And then we would multiply it by our circumference formula, which is 2 pi times the radius. And this would get me the length of this arc, okay? So it gets a lot easier to figure out arc length in terms of radians as opposed to in terms of degrees, okay? Because remember, our radian is the measure of that central angle that's equivalent to the radius, right, of the arc length. So if we use this same concept, but now we're flipping it to radians, it's a lot easier of a formula. Okay, so from geometry, we know that the ratio of the measures of the angles equals the ratio of the corresponding side lengths of the arc subtended by these angles. So that is, we have theta, so here's our central angle theta, is proportional to theta sub 1, let's say. And then that proportion, or those ratios, would be equal to the proportion, or the ratio of S, so the arc length, given theta as a central angle, to S sub 1, which would be the arc length given the central angle of theta sub 1. So if we let theta sub 1 equal 1 in this proportion, so that would become theta over 1, and S sub 1 is going to be equal to R from our previous definition of a radian, so S over R. And I want to solve this out for S. Multiplying by R on both sides gets us S is equal to R times theta, right? Which is where this formula comes from. Okay, so you are going to want to memorize this formula. It's not very complicated. So your arc length is equal to the radius times theta, as long as theta is in radians, never in degrees. Because if it's in degrees, then we have to do degrees over 360 to figure out our fraction of it, and then multiply it by 2 times pi times r. Okay, but it's much more simplified if we just do radius times our central angle in radians. Okay, so that's why we got to be able to convert back and forth between radians. So for our first example, example number 1 here, it says, given a central angle of 60 degrees and a radius of 8 centimeters, find the length of the intercepted arc. So the first thing we have to do is we have to convert our degrees to radians. So 60 degrees, remember our conversions, we multiply by pi over 180 degrees, right? So that gets us 1/3 pi would be our radians. So now using our formula, so our arc length S is equal to our radius, which they told us is 8, times our central angle in radians, which is pi over 3, which is 8 pi over 3, right? So that would be in centimeters, because that's my dimension. So what's that equivalent to if I actually want to get a decimal version of that? It's approximately 8.377 centimeters. Okay, so in this, I guess I should have drew this out first. So here we have a 60-degree angle. We have 8 centimeters. So I could technically do 60 divided by 360 times 2 times pi times 8, right? So 60 over 360 times 2 times pi times 8 times your radius, right? So if we think about that, what did we just do? 2 divided by 360. Isn't that 1 over 180? So now don't I have 60 over 180 times pi? Isn't that our conversion right there for our, oops, over here? Isn't that what we did to get to our radians? Yeah, we did, right? 60 divided by 180 is a third times pi, so 1/3 pi. And then multiply by your radius. Okay, so they're the same thing, just one's in radian form and one's in degree form. Okay, so there was our answer right there. Let's do another one. Example 2. If a 100-degree arc of a circle has a length of 9 inches to the nearest inch, what would be the radius? So now we're doing it in reverse. So now we're being told that my arc length, S, is 9. We need to solve for R, and we have theta, right? So we need to solve, well, we need to solve for R, but before I can do anything, I need to convert my theta into radians. So we have 100 degrees. Let's do that conversion. So 100 degrees times pi over 180. So that goes to 5/9 pi. So this is our degree, or sorry, our theta in radians. So let's plug that in. So 9 equals R times 5 pi over 9. Right? With me so far? So now let's solve this for R. So multiply by the reciprocal. 9 over 5 over pi. I guess it wouldn't really matter. Right? Yeah. Times 9. Gets us R. So 81 over 5 pi is equal to R. So my radius is 81 over 5 pi inches, which is approximately 5.156 inches. There would be our two answers to the nearest, round to the nearest inch. So 5 inches. Good. So what did we just do? So we had a 100-degree angle. We had to find R, and we were given an arc length of 9 inches. Okay, example number 3. Find the angle in radians, then convert to the nearest degree. All right, so what do we have? We have to find theta is what we're looking for, right? We have the arc length, we have the radius, we need to find theta. So S is equal to R theta. S was given to us as 8. Our radius is 5. Solving for theta means that it's 8/5 radians. Okay, because remember this was radians to start out with. If they gave us the actual arc length, then it was in radians. So now we need to do our conversion of that to degrees. So radian to degrees. We take our 8/5 radians, multiply by 180 over pi. Because remember, when you're going to degrees, you want to divide out the pi. Right, so now you just have to do that math. So 1/5 times 180 over pi should get you approximately 91.673 degrees. It's asking you to go to the nearest degree, so about 92 degrees would be your answer there. Okay? Alright, so arc lengths and radians. Whenever you're using that very simple formula, the catch is theta needs to be in radians. Alright, moving on down to circular motion. Here we go. So, linear velocity. If you guys remember the video of the teacher swinging his keys, and he was talking about all those tangent lines going around the circle of those keys. Those are your linear velocities, right? So, have you ever thought about math while out for a bicycle ride? Probably not. You know how to find your average speed by calculating distance traveled divided by the time from long ago. Rate equals distance divided by time, right? or r equals d over t, or d equals rt, right? So in trigonometry, we call this linear velocity, or speed, and rename our variables using v for velocity, or your rate, and s as your arc length for distance. Okay, so this is where we have the following formula. So your linear velocity is v is equal to, remember delta is change, your change in s over your change in t, where delta s then would be equal to v times delta t. Okay, so let's go ahead and put this into practice. So dimensional analysis. If you travel in a car at 65 miles per hour, how far did you go in 10 seconds? All right, so velocity is equal to, right, we're going 65 miles per hour. So 65 miles per 1 hour. Right, and we want to try to get it to, well, we want to do 10 seconds, but we need to do some more conversions, right? Because I want to get this to seconds, miles per seconds. So we know that 1 hour is 60 minutes, and we know that 1 minute is 60 seconds, right? So now I'm getting my hours to cancel out, I'm getting my minutes to cancel out, so I'll be left with miles per second. And the reason why I'm doing this is because I have time in seconds. So that gets us to, when you do the math, 0.01805 miles per second. All right, so now we can go to our formula. So we know that, right here, our S, right, okay, our speed is equal to velocity, our rate, or sorry, not our s, our distance. I should not have said speed. Our distance, right? Distance, our arc length. S is equal to our velocity, our speed, times time. So S is equal to our velocity, which was 0.01805 miles per second, times 10 seconds. Now notice how your seconds would cancel out and you would be left with just miles. So when I multiply that, I get 0.1805 miles. So my distance, my arc length, S, not speed, velocity is speed. S is our arc length, is equal to 0.1805 miles. Okay? All right, so there is our answer for example 4. So that's linear velocity. So just straight linear. Now when we get into angular velocity, which means we're going to be going around the circle. Okay, so now let's look at another type of velocity while we ride our bicycle. Think about how fast the wheels are rotating. This is called angular velocity. And we use the Greek letter omega as the accepted variable used for angular speed. This is the rate that measures changes in the wheel's central angle theta over time. So here we have our formula. So omega, which is our angular velocity, is equal to delta theta over delta t. And then if we solve for our theta, it's equal to our angular velocity, right, times time. So our distance around, right, our theta is our central angle, is going to be equal to those. Okay, so here we go. Example 5. Let's do this in practice. If a central angle spins 15 pi radians in 8 seconds, how fast is the angle spinning per second? So if a central angle spins 15 pi radians, okay, so 15 pi radians is our central angle. Oops, I'm not writing. Central angle right here. So this is our theta in 8 seconds. So there's our time. How fast is the angle spinning? So we're looking for omega, our angular velocity. How fast is the angle spinning per second? So omega, angular velocity, is equal to our central angle, which is 15 pi radians, which is good because I need that to be in radians, divided by our time, which is 8 seconds. So this is radians in our numerator. So that gets us 5.8904 radians per seconds. Okay, it said round to the nearest thousand. So 5.890 radians per seconds. Okay, all right, so angular velocity, linear velocity. Make sure you have the difference. Angular velocity, you do your central angle divided by time, right? Linear velocity, you do your arc length or your distance divided by time, right? Okay, so on to the next page. Units and converting between linear and angular. So your forward velocity summary. Linear velocity has dimensions of length per unit of time. So examples are such as feet per second, miles per hour, meters per minute. The numerator units are always a measure of length. It's a good way to think about it. Angular velocity has dimensions of angle measure, radians per unit of time. So examples such as revolutions per minute, radians per second, degrees per hour. So the numerator units are always going to be angle measurements. So converting units of angular measurements. So if I had to convert 60 revolutions per minute to radians per minute, how will we do that? So my omega is equal to, 60 revolutions per minute. Okay, and we need to get it to radians per minute. So minutes are already in there. So now let's do our revolutions. Well, what is one revolution? We want a revolution. Nope, not that type of revolution. One revolution, remember, is 2 pi radians all the way around our unit circle. So now my revolutions are canceling out. And won't I be left with radians per minute? Yeah, I will. So omega is equal to 120 pi radians per minute. Okay, so if I needed to convert 60 revolutions per minute to degrees per second, how would we do that? So 60 revolutions to 1 minute. Okay, so now we're doing degrees, right? So now I got to go to degrees. So 1 revolution is not 2 pi radians. In degrees, it's 360 degrees. And now we got to get our minutes. So cancel out your minute. So 1 minute is equivalent to 60 seconds. So revolutions cancel, minutes cancel. What am I left with? Degree over seconds. Multiplying that straight through gets me 360 degrees. Actually, degrees per second. Good. Sorry, my handwriting is terrible. I think my daughter had some grossness on her fingers because there's all sorts of grossness on my screen of my iPad. Okay, so important relationships between linear and angular speed. We can use the previous formulas to find a relationship between linear velocity and angular velocity. So we have our linear velocity formula. Now remember that your arc formula is S equals radius times your central angle, which is in radians. Okay, so if I substitute that in place of here, so this is going in place of S, r theta. Do you ever see where that came from? So if S is equal to r theta, then that becomes r theta over t. And then if we wanted to keep on simplifying that further and factor out an r, I don't know how that's factoring out an R. All right, sorry, I just had to get my brain back into gear. I got confused on what the word factoring is. If you take out the R, right? Then you would have r times delta theta over delta t, is what this step is right here. And what does this actually represent? Well, doesn't that represent our angular velocity? Yeah. So really our velocity is the same as taking your radius. Our linear velocity is equal to taking the radius times your angular velocity, which is where this relationship comes from. So linear velocity is equal to r times your angular velocity. All right, so some more formulas we need to work through. Area and distance. So area of a sector. So now what we're talking about is the actual area of a piece of the circle. So if you guys remember back in geometry, finding the area of this whole section. So if this was, let's say, 60 degrees, and this was 4 inches again, let's say, we would do 60 over 360 times the area of the whole circle, which is pi times the radius squared, right? Okay, so again, we're going from radian or degrees to radians, which is where this formula is going to come into play. Because if I think about that, if I convert it, my 60 degrees into radians, I would do times pi over 180, right? Okay, so here's our formula. Get rid of that. So our area of a sector, instead of doing it with degrees and in radians, we just take 1/2 times your radius squared times theta, which theta needs to be in radians, never, ever, 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 ever in degrees. So find the area of the sector of a circle of a radius of 2 feet formed by an angle of 50 degrees. So let's do our conversion for 50 degrees. 50 times pi over 180, which is equivalent to 5 over 18, right? 5/18 pi. I don't even know why I picked up a calculator for that. So my area is equal to 1/2 times my radius squared, so 2 squared, times my central angle in radians, which is 5 pi over 18. And when you multiply all that out, 2 decimal places it's asking for, so 0.75. Remember, area is always units squared. So 1.75 units squared. Okay, again, much more simpler when you're using it in radians as opposed to degrees. Finding the distance between 2 cities. Memphis, Tennessee. Okay, so we have Memphis, Tennessee is located at 35 degrees 9 minutes north latitude, and New Orleans, Louisiana is at 29 degrees 57 minutes north latitude. So assuming that the radius of the Earth is 3,960 miles and the cities lie along the same longitude, find the distance between the 2 cities. Okay, so this is what we have happening. We have the 2 cities. Oops, I'm not even writing right now. Give me a second. So we have the equator, right? We're going to call this my equator. We have New Orleans is, let's say, right about here. Okay, so, yeah, New Orleans is the first one, or the closest one. So 29 degrees 57 minutes would be New Orleans. And then we have Memphis, let's say up here, at 33 degrees 9 minutes. Oh, I have the wrong tick marks. Well, single tick marks. Minutes. 57 minutes. Oops, there we go. All right, so now, what are we looking for? So we are looking for the angle between the 2 cities, which is going to be right here, right, is going to be theta. So the angle between the 2 cities is equal to theta. All right, so let's figure that out. So theta is going to be equal to 35 degrees 9 minutes minus 29 degrees 57 minutes. If I do that conversion to degree decimals, it's about 35.15 degrees. minus 29.95 degrees. I got the 0.15 by taking 9 divided by 60. I got the 0.95 by taking 57 divided by 60. So that difference is approximately 5.2 degrees. Converting that to radians is 0.0907 radians. How do we convert to radians again? Oh goodness gracious, there we go. Right, we take 5.2 times pi over 180, right? To do our conversion, that's where the 0.0907 would come from. So we're looking for the distance between the two cities. So notice my distance between the two cities is pretty much an arc length, right? So my arc length is radius times theta. We were given a radius of the Earth at 3,960 miles. And my radians were 0.0907 radians. So when we multiply that together, we get 359.172 miles. There we go. So our final answer would be that Memphis and New Orleans, or New Orleans, however you say it. I'm so sorry, I thought I just silenced this. New Orleans are about 359 miles apart. Okay? Alright, almost there. One more example to get through. Okay, so example number 9. We have area and distances happening again. Some earthly discoveries. So compute the length in feet of an angle measure of 1 minute on the Earth, given that the radius of the Earth is 3,960 miles. Okay, so compute the length in feet of an angle measure of 1 minute on the Earth. Okay, so we got the Earth doing its little, think about it as a circle, right? So 1 minute on the Earth. So theta, remember, is our central angle. Right now we're in 1 minute. Well, that's just a really, really tiny form of degree, right? Okay, so how do I convert that? Well, that's the same as 1 over 60 degrees is 1 minute. Converting that to radians, so multiply by pi times 180 gets me pi over 10,800, right? Okay, so we want to find the distance, same thing as the arc length, the length, right? My radius, so 3,960 times my central angle in radians, which is pi over 10,800. So that's 11 pi over 30 miles, which is equivalent to 1.5 or 1519 miles. So the length in feet of an angle measure of just 1 minute on the Earth is equivalent to 1.1519 miles. Okay, so 1 minute, if we summarize it, 1 minute is about 1.152 miles on Earth. If we think about the goodness, there we go. The revolution of it, right? All right, so for 9b, what is the length of an angle of 1 second on Earth? Okay, so we're going to do pretty much the same thing, but now we're going to a second. So theta, right now, is giving to us in the really tiny, tiny part of degrees. So that's 1 over 3,600 degrees. Converting that, pi over 180 gets me pi over 648,000 radians. So my length is equal to the radius of 3,960 miles times my central angle in radians. So pi over 648,000 gets me approximately 11 pi over 1,800 miles, which when we round that out, it's about 0.01919 miles. So 1 second is about 0.019 miles, or to make more sense of it, if I can do the conversion to feet, that's about 100.137 feet, which makes a little bit more sense in our minds, right? If I thought about it as feet instead of 0.019 miles. All right, this concludes your notes.